Shall we start? Okay. Well, ladies and gentlemen, I think it's this time at the meeting where all good things have to end, and hence we have the last session, but may I add that we left the best for the last. And hence it is my great pleasure to introduce my colleague and friend, Professor Carlos Santamarina. And I'll try to tell you, of course, some of the obvious things which you can find in Wikipedia and Google Scholar, but I also will try to say a few things that will hopefully get him closer to you as a human being. So Carlos was born in Cordoba, Argentina, went to school and high school, a Jesuit one there. And these schools taught him to understand and love humans. At the same time, of course, in Argentina, you had the Operation Condor and the right-wing crazies killing people by the tens of thousands and disappearing other people. So obviously there was a dichotomy between love and hate there. So Carlos got his BS degree in civil engineering at the Universidad Nacional de Cordoba in 1982. And then he went to the US permanently. He got his MS at the University of Maryland and PhD at Purdue University in 1987. And then he immediately became a professor because that was his calling in his life. And he taught at NYU, University of Waterloo, and Georgia Tech. And then he did something unusual for a very successful faculty at a very successful university. He left it and went to another country to establish a new program and a new lab together with me. I was the first one hired by KAUST in Saudi Arabia to open a new center in petroleum engineering and shape the program, hire the faculty, get the equipment, and so on. And for those of you who haven't done this in your life, or in your lives, I must add that this is a unique experience that is very difficult to translate if you enter a young university with unshaped programs and everything is so desirable and in the future, and you make it happen. And that's what Carlos and I did over the last 8 years, and I might say with some success. And now Carlos decided to go back to his old school, Georgia Tech, where he actually reopened his old lab, which waited for him all these years. So now let's go back to the usual. So Carlos is a co-author of hundreds of papers, over 400, and 2 books, which are very popular. He is a born experimentalist. And when I say that, I say it very seriously. He thinks in terms of experiments. And in his research, he follows physics as an inspiration, and then he collects data, and his large student group and researchers, some of whom are sitting here up front and smiling at me, are trying to decipher how nature works and then put it into elegant models and elegant demonstrations. And so he works on the flow in porous media, multi-phase flow, multi-physics, multi-everything, fractured rock and complex fluids. And of course, he also focuses on the subsurface energy storage and all the good things that happen there, including oil recovery. I will close by saying that we have become friends, and he's greatly missed at KAUST, not just by the faculty, but also by the students and the researchers. But with that, I let him speak, and all the best.
Thank you so much, Tom. Thank you, and I have to say I'm so pleased to see you all still here. And thank you for staying and for giving me the opportunity to share some thoughts with you. This is kind of a hobby that we began building many years ago, and there are research pieces here that will come together in this puzzle for the last 25, 30 years. And I put it together for the first time for this presentation, and I hope it works out. So this is the idea. What happens when porous media are subjected to repetitive multiphysics loading? And that turns out to be quite a common event. And as I said, many people have collaborated throughout these years, and I'm so grateful to all of them. You will see the results. Some of them are here at InterPore. And I also have to say that this has been possible thanks to the great institutions that I have been part of and the funding agencies behind this. So folks, take a look at this, and you see so many dynamic systems that are repeating themselves from running in the International Space Station to barometric cycles to a silo being loaded and unloaded, or Masada Mountain subjected to fairly pronounced thermal changes, or the foundation of a wind turbine, or a major hydroelectric project, pump hydro, where the water keeps going up and down, loading and unloading the system. And in fact, there were many examples this week on cyclic processes. And unfortunately, I don't think we paid enough attention to them, because we tend to teach and conduct research assuming that everything is kind of monotonic. But this is quite a common realization. So I'm going to start with this first few, and then we'll do the others where the matrix, the porous matrix, comes into the picture. So let's start with these two. And the story of the bones is amazing, because there was somebody making a presentation in the mid-19th century, and Kuhlmann, who in civil engineering is very well known because he was designing cranes, he realized that the cells in the bones in the head of the femur were pretty much following the lines that he would have put trusses to support structures. And that opened up this idea that the bone is actually growing following some instructions from the stress field. But how does that happen? Well, it took another century, and it wasn't until the last 50 years that we kept thinking that the nutrients to bone cells are going through by diffusion. But as it turns out, if it was diffusion control, we would have all massive osteoporosis. And so how does it actually happen is where the story begins. And so let's take a look at this tube, and there is a red fluid and a blue fluid. If I push back and forth, nothing much happens. I know you can get a little bit pickier on this, but let's just play the game. Now, what happens if not only I have a tube, which we're going to call it a canaliculae, that's the term they use in the bone field, and there are pores in between, which we're going to call them lacunae, like little lakes, large pores. So now the fluid goes in, it mixes with the fluid, the red fluid, it mixes with the fluid, the blue that was already in the pore, then it backs off, but some color remains. In the next cycle, it gets pushed a little further away, and then it returns, and then it gets pushed even further away. So by cycling back and forth and mixing, all of a sudden I have very effective species transport mechanism. And so we were curious about it, and so we did some of the mathematics, and if you make some asymptotic approximations, voila, you end up with Fick's law. But the coefficient is a completely different coefficient. The coefficient, I don't have a pointer, so you have to follow my words to see where I am. Oh, there is a pointer, not on the screen, so at least those who may be watching will miss it. But you see, there is a diffusion coefficient, but the diffusion coefficient is related to the properties of the cycles that you are imposing. There is a characteristic scale, the characteristic scale of the bone, the distance between lacunae, L, and there is a time of the cycle, and there are some geometric effects. So that is the effective diffusion coefficient. And how effective is it? So we run some experiments. This looks like a heli show where we are going in and out, and blue fluid begins to gradually invade, and it does it very effectively. And so then you can measure and plot and compare against the standard diffusion coefficient, and My goodness, it got really effective. Several orders of magnitude. And by the way, that is injecting in and out. What the bone actually does is a sponge that you squeeze in and out. So you have to think of biot type of a formulation. And when you do that, you come up with a slightly different diffusion coefficient now for a flexible matrix. And there is no flow through. So it's plugged at the end. But we also have a fairly effective diffusion coefficient. Once again, there is a length scale and there is a time scale, which is the one that you impose in the cycles. Once again, orders of magnitude improvement in transport. Now, if water goes in and out and is allowing us to transport the species, now imagine that I inject hot water in and I pull it out, hot water in, and every time it goes in, it transfers some of the heat to the matrix. Then when it comes out, the water above it comes to the hot matrix, picks up the heat, and when you push back in now, it goes a step further up, which is what the sketch on the left, the sequence of sketches on the left are trying to show. So that seems also an interesting idea. So we can transport not only species, we can also transport heat. And so, but first of all, let's realize that there is an inherent internal time scale. So let's explore that. We take a ball, we put the thermocouple inside, we dip it in cold water, we let it homogenize, and then we go into the hot water. It's a trivial experiment, I know. Excuse me. From the hot water, we go into the cold water, and you see how it gives this energy back to the pool. And from that, you can come up with some form of a characteristic scale. It's not pure an exponential process, but let's say that we take the typical time scale of an exponential decay. And so that is the time scale for heat exchange for a single grain in this fluid. And so when we do the mathematics now for the fluid invasion and pulling in and out, we come up again with a diffusion equation. And once again, we have the length scale, which is the penetration of each cycle, and the time of the cycle. And there are a few other components which relate to the specific heats and the relative mass fractions of the components. And we run the test, we put thermocouples in a granular base all the way above and then at different heights. And we see how the heat front propagated, and indeed it did it very effectively. And so, for example, here in this room, if we don't need to make it cooler, we could increase and decrease the pressure and your clothes would be breathing better. Your ears would hurt, but the concept is I'm trying to project. Now, what happens when we breathe? And we saw Adrian Bejan showing us a beautiful presentation yesterday, but I'm going slightly different. I want to see what is happening in the alveola at the end of all this, where the exchange of CO2 gets out, the oxygen gets in, the alveolar water saturated. And so at that interface, you have surface tension, let's say the 72 millinewtons per meter. But if that was the case, when you breathe out, when you exhale, the alveola contract, it would be very difficult to breathe back in. The thorax, the diaphragm will have to make a very large force. In fact, some babies are born without pulmonary surfactants, and they have to inject pulmonary surfactant right away, otherwise their lungs collapse. And so, yes, that is the trick. There is pulmonary surfactant. That will come in the next section. So what I want to say here is that every time we breathe in and out, air goes in with a low relative humidity. Imagine a winter night with heat in the room, the relative humidity may be 30%. When you exhale, the relative humidity, the air is fully saturated. It's almost 100% relative humidity. So that means that every time we inhale and exhale, we are losing moisture in addition to losing the carbon. And so you can check it yourselves. You are something like 200, 300 grams lighter when you wake up in the morning. And most of the loss is because of exhaling and losing water and some of the carbon. And so we reproduce that to see what happens. How does the soil layers above in the Bedos zone are interacting with barometric cycles in the atmosphere, which is exactly the same process. And so we tried it. And so we put this cell unsaturated because the gas has to go in. So you want to be at the saturation below the air entry point. Otherwise, it just goes to to the saturated level. And so you see the initial profile on the right, and then as we have gone in and out multiple times, we have replaced 100 liters of air. You see how it's drying, and it dries very effectively. And on the right-hand side, you see the rate of mass loss against the number of cycles. And from the gas law, you can compute how far your dry air penetrated, because you're still squeezing the air that was originally inside. Very effective. Now imagine, and Jose Davalos here is doing that, you may not only exchange moisture, you may also exchange the CH4 for CO2. Or you can begin cycling many of these and trigger reactions with some characteristic internal time scale. It's like a Darmstadt type of scaling. Now, this is where the surfactants come back. And so you see the surfactants when the alveoli are contracted. You see that the surfactant molecules are very close to each other. And so the surface tension is very low. When you exhale, the surface tension goes down to something like less than 10 millinewtons per meter. And then when you inhale and the alveoli enlarge, the surfactant molecules are further away from each other, and you go pretty much close to the 72 millinewtons per meter. This is an amazing self-regulation. When you exhale, the lines are ready to contract, and when they are contracted, they are ready to expand, so the thorax, the diaphragm, doesn't have to work so hard. And that makes you wonder, does this happen when water with surfactants goes through pore throats? And so we tested that. And this is the water with surfactants going through the pore throats, and depending on the concentrations, etc., you get signatures which are completely different than you would expect from your theoretical analysis based on the contact angle and the constant surface tension. And Haynes jumps are going to manifest differently, etc. But these molecules can live out and form micelles, and then you say, but if there were nanoparticles at the interface, they have a high adsorption energy, they won't dissolve so easily. So what will happen? So we tested that, and that is a droplet at the top on the left. It looks like a Laplacian surface. As we begin contracting, oops, wrinkles appear. Totally unexpected from a water oil system. And those wrinkles continue increasing, and this is what has happened, is that there has been a self-organized structure around that forms a shell, but the shell with a diameter much, much larger than the particle size, and is so well organized that it actually reverses your capillary pressure. I mean, talk about the Roman arches. This is amazing. And then by the time we begin expanding it again, it preserves some of the shell, and you see those crevices, and look, it looks almost like a cylinder until it finally breaks through and it goes back to a Laplacian surface. And now when we cycle that, the particles are beginning to get more and more compacted. And so you're making this shell thicker and probably multi-layer and more compact, and the transition from a Laplacian to a Newtonian shell type of a structure begins to change. Cycles, pore throats. Well, the astronaut also running on the treadmill, not only was breathing and exercising the femur, was also the heart was beating. And look at the heartbeat. This is the pressure in the ventricular of the heart, and this is a true positive displacement pump. I mean, we have so many peristaltic systems in our body. The whole GI tract is a peristaltic system. So it's not that nature doesn't know how to make a peristaltic pump, but our heart is a positive displacement reciprocating pump. Why? And we wonder, we don't have the full answer, but they have, in all these artificial heart machines, they have shown that there are problems with continuous pumping. And so we're going back to reciprocating pumps. And so that gave us an idea, because we accelerate the flow and then we relax it and then we do it the same. And by the way, that's the way jellyfish work. And you can say, well, the excitation, after all, is a Fourier, is a sum of sinusoids forming a beat function, an asymmetric function. And however, the response is nonlinear, so this is non-convolutional process. And effectively, that's the way we swim, with asymmetries. And so Dr. Abdelaziz here have us put some particles in a tube, And he began injecting fast and withdrawing slowly. Injecting fast, withdrawing slowly, that's the way we swim, and we transport particles very effectively. Not surprising, but it does work. So there is zero effective liquid transport. The cycle average is zero. However, the solids are gradually moving forward very effectively. And you can think what happens in a linear system versus a radial system. Let's say if you do this from an injection well, of course, you lose velocity with distance. And so it happens in the body as well as we go into the network of arteries. But there are also asymmetries related not only to the excitation, but to the hysteresis in material response. This is a small water droplet in a capillary tube. You have the advancing and the receding angle. They are not at limiting conditions because probably the droplet is not heavy enough. And now what we can do is we can excite it asymmetrically. I tap it against the block at the bottom, or I tap it at the top, and I can move that droplet up or down as I will. And I do it the same, starting from an equilibrium horizontal position, and it moves left and right. And these tests, we did them way before high-speed photography, so we were doing it with a stroboscopic light. And we move the droplet left and right. And so we can move ganglia. There is a little bit of a quantum jump from these capillary test tubes to the full field, but the concept is what I'm trying to suggest with cyclic excitations. So let's take that as the first part of the presentation. Let's address the other 4 cases where we have an interaction with the matrix. And the reason for this is because energy is always coupled. And so that comes from the first law of thermodynamics and Le Chatelier's principle that tell us that nature will do anything it can to oppose change. And when you put the two together, then you put a mechanical action and you will have a reaction on the other 3 or 4 and vice versa. And they're all fully coupled. And that is the old elastic band example. You stretch it, you feel it with your lips, and you feel that it's warm. So the thermoelastic effect. Now, that is from thermodynamics, which justifies everything but doesn't explain much. And so let's see what is the actual cause. And the actual cause is that, let's say, in granular media, I try to bring it to an example that we can all grasp, is all about forces. If particles are going to move, there is a force, there is an acceleration that is integrated, and there is an unbalanced force. And so what are the forces acting on a grain? And we have the force because the particle is part of a big skeletal, granular skeleton, because it has self-weight, buoyancy, hydrodynamic, let's say, Stokes type of drag, capillary effects, electrical attraction and repulsion, let's say the DLVO components, thermoelastic, and cementation, which is really a passive force, and you can think of other forces that could come into the picture. What I want to highlight is that I can find power functions for all these, that they are either linear, quadratic, or cubic. And that's very nice because if I plot them in log-log scale, they are straight lines that they are going to intercept. And when I do that, there are some interesting consequences of this analysis. For example, the intersection between self-weight and the maximum capillary force between 2 sand grains happens at about 2 or 3 millimeters. We cannot make sand castles with coarser sand. The intersection between the stress carried by the force carried by a particle when it is part of a packing subjected to 100 kPa is equivalent to the maximum capillary pressure force that it can feel under unsaturated conditions at about 2 or 3 microns. In order to incorporate the electrical forces, I have to actually create a scenario where, let's say that I have all the particles in equilibrium, in a dispersed form in equilibrium under 100 kPa, and then I change from fresh water to deionized water, from deionized water to salt water. And you're going to change the osmotic pressure, shrink the double layers, they are going to contract. What will be the strain that causes? Well, there is no strain, basically no measurable strain when the particles are much coarser than a micron. And so now we begin to recognize the ranges where all these forces become important, and that will shed some light in the next few minutes. But if I compare the thermal forces, thermally induced by temperature changes, and the skeletal force, something interesting happens. They are both functions of d squared, so d cancels out. That means that thermomechanical effects are going to be relevant at all scales. And so I will give you some examples of that. So let's start with some chemical cycles. I'm going to change the fluid in and out to change the double layer thickness and the repulsive forces. I'm creating a change in DLVO components. And as I said earlier, if you have a high specific surface material at low confinement, these changes can be quite brutal, 30% volume contraction. If you have a silt and it is at high stress already, the contacts are quite deformed, these are going to be very small strains. And our shales or sandstones, etc., are going to be somewhere in between. So let's run the following experiment. It's a difficult experiment to run because the time scales are long and because you want to change the chemistry without changing the mechanics. In other words, I want to change from one fluid to the other without ever depressurizing the system, so I don't change the mechanical Terzaghi effective stress. So that's what we do with the setup that you see on the left. We have a valve that we switch from left to right. And as we let the brine go in, the sample contracts, fresh water goes in, there is some swelling, another flash of brine, the red line, it contracts again, etc. And it goes towards an asymptotic state, but with very pronounced chemical stress changes. So imagine that with sea level rise, there will be saltwater intrusion. Some of these processes are actually going to be taking place in our cities and coastal regions. What happens with wet and dry cycles? Now I live in Atlanta, and every driveway in Atlanta is cracked. And we tend to think because you run heavy trucks on top or not. I'm convinced that it's because of wetting and drying. And so let's explore some of that. At the top, you see a picture of two glass beads with a large meniscus, a small meniscus, and we can do all the computations. And we do that in a vessel, salt confined, while at the same time we change the relative humidity. And once again, significant volume contraction going to an asymptotic state. How can we explain it? This Terzaghi effective stress plus some changes. This is not a pure version for unsaturated salt behavior, but that's called Bishop, which is the last part of the upper equation is the UA minus U water is air minus water. That is the capillary pressure that I'm oscillating. So I'm changing effective stress through the suction, through a capillary pressure. And I'm accumulating changes in the void ratio. And if you see when I goes to infinite, the second term vanishes and the void ratio goes to a terminal void ratio. So there is a terminal condition, and having asymptotes is wonderful for engineering design. And so there is a terminal condition here. What happens with freeze-thaw cycles? I saw a couple of posters and presentations on that in this conference, so I added these slides. So we have once again a specimen, the one in red color, I guess, or orange color, surrounded by a coil that we use to freeze the system with surrounded by anti-freeze. The cell is loaded isotropically and some deviatoric load. In other words, I'm taking a specimen from a sloping ground. And so then, okay, I will use the pointer this time, okay? Then you see how the system evolves. We begin cooling, the temperature goes down, supercooling, finally begins nucleating ice, so it jumps to the phase boundary, the 0 degrees Celsius, and then when all the water is frozen, it keeps cooling, following the bath, and then we reverse it. By the way, notice that in kaolin, it happens very much the same, except that here, there is not a sharp boundary because now we are beginning to have the pore size effects that even are present in kaolin, the phase boundary shifting on us. What I would like to highlight that these two soils now behave completely different during phase transformation. The sand, the ice is forming within the grains. In the clay, ice is displacing the grains. So in one case, the phase transformation is pore invasive, in the other one is grain displacive, and we form the well-known ice lenses. So the effect on cyclic loading, which we may experience now with climate change towards the polars and subpolar regions, is going to be quite pronounced when we have fine-grained sediments. And let me show you the example. Now this explains what is happening to the fabric. Once again, in sand being pore invasive, and the blue in this case is the ice, everything is water saturated. In the clay being grain displacive, and in addition with a cryogenic suction, it compacts the clay. By the time you thaw it, if you allow the water to drain, the whole system will compact quite extensively. If you don't allow it to drain fast enough, which is happening during the spring, then the water cannot escape, and those ice lenses now are going to be water lenses, and you're going to have massive failures. And indeed, that is what is happening. And this is telling that with experimental data. So the other effect, I said earlier that I was going to show you the fact that thermomechanical effects are prevalent at all scales. We have tested it for clay, the sands, etc. But take a look, these are big boulders. And let's see what happens in this case. Imagine that during the day it gets hot, so the whole block expands. At night it cools, and the choke blocks on the back may fall down a little bit. Then it expands again, but because the choke blocks are holding it from the back, it can only expand forwards. And if it goes above the threshold level that will produce some slippage at the boundary, then it will move forward, and then the choke blocks will come again, and now we begin having a ratcheting effect. And indeed, that is happening. Take a look at some of the blocks, the Eugenia Canyon. Take a look at that wedge, and the passive block on the left is actually tilting already. This is the Grand Canyon. We have wedges. This is Masada Mountain. I mentioned that one before. An amazing part of history. The blocks are moving. There are string gauges. They have instrumented, our colleagues in Israel have instrumented. So these are displacement transducers, and it's moving, and they cannot relate it to rain, that is on the Dead Sea. They cannot relate it to earthquake, that is a fairly passive area, and they are moving. And in fact, it's because of thermomechanical effects. And you see the choke block falling behind. And this is in Saudi Arabia, a beautiful part of the northeastern Saudi Arabia, northwestern Saudi Arabia. And you see that block, you see the failure plane there? And you see the choke blocks, and in fact on yellow, you see that it has already actually displaced quite a lot. And so we actually tested experimentally. This is true experimental data. You have the resistance, the passive voice, and the block and the choke block in a chamber where we oscillate the temperature. You see the thermal oscillation on the left in red, and you see the displacement of the block in blue at the top. This is ratcheting its way down, and it's happening in nature. It's happening at all scales. You do the mathematics, and you can see what is the temperature, the threshold temperature for this to happen, and you have all the parameters involved there. By the way, the hint, it doesn't happen with diurnal changes. It tends to happen with seasonal changes because you need enough time for the heat to penetrate the rock and for the expansion to be more pronounced, for the displacement to exceed the threshold level of displacement. We're approaching the end. I want to say now that the hydromechanical coupling, I'll tell you the story. The story is the story of the Tower of Pisa. If you look very carefully, it's hard to tell on the image, but if you look very carefully, by the time they got to the third floor, the tower was already tilting. And the builders were so good that they decided to realign the columns a little bit. So the second half of the tower would look a little bit more straight. But it kept tilting. And the fact that it was tilting means that it was already at yield. It was already yielding. It was already approaching at the verge of failure. Okay, but you slow down the construction, the excess pore pressure dissipates, you gain some stability, you put another floor, but then water was being pumped from the piazza. And now let's see what happens. This is a tau sigma, more Coulomb space, QP tau sigma. And the thick dotted line is a Coulomb failure, tau equals sigma tangent phi, that is that line. And so we put it under a state of stress equivalent to the foundation of the Tower of Pisa, and then we begin increasing and decreasing the pore fluid pressure to simulate pumping. And so this is a test, the specimen and the deviatoric and isotropic loading plus some deviatoric loading, sigma 1 and sigma 3, and then we begin changing the pore fluid pressure, and very significant strain buildup in every cycle. And in fact, we might as well mention Leonardo, who was throwing things from the tower, and Leonardo made that drawing, that is a ratchet. And so, rightfully so, this phenomenon is called ratcheting. The closer you are to failure, the higher the chances that the porous matrix will ratchet with all these cyclic processes. Imagine that you are next to a fault and you begin cycling the fluid pressures. Now, not only there will be shear displacements, the volume will also contract. We saw that at the scale of nanoparticles on the surface of droplets, but this is also happening in the subsurface beneath our feet. And we reproduce this case now by loading specimens, and we load and unload, and you see that the volume decreases, but the volume cannot vanish. So it goes to an asymptotic value. So from a shear deformation, you can accumulate shear forever. From a volume deformation, you reach an asymptote. So when we put all this together, this is a fourth dimensional space. These are the projections. So let me go back, and here is tau sigma. This is the more Coulomb space. This is shear versus shear strain, and it could either stabilize or continue accumulating ratcheting mode. But from a volume point of view, it has to reach an asymptote, which we call terminal void ratio or terminal density. There is a little lesson here to be learned. These accumulations are taking place even at very, very minute deformations. If you think of two grains, for them to move relative to each other, the relative displacement has to exceed an angstrom. You have to break an atom. You have to break a bond, not an atom. You have to break a bond, let's say 1 angstrom. And let's say that the particles are 1 millimeter. So between two particles, you want 1 angstrom displacement, you need to have a shear deformation of 10 to the minus 10 over 10 to the minus 3. You need to have a shear displacement of 10 to the minus 7. We are getting strain accumulations with 10 to the minus 8, 10 to the minus 9, which is unheard of. People in liquefaction and earthquake engineering couldn't visualize this. But what is happening now is that these slippages are not taking place at every contact. They are taking turns and sporadic here or there, and there is a gradual rearrangement, and you can subject these to millions of cycles like the basis of a wind turbine. So it's time to conclude. Repetitive loads are ubiquitous, a word that I shouldn't put how to pronounce. Repetitive loads are everywhere in nature and in engineered systems. And they are because of hydro, thermo, chemo, crystallization, suction, interfacial, mechanical, etc. processes. What is the causality behind? Well, in part is energy coupling. In part is asymmetric excitations, but it's also because of the hysteretic nonlinear behavior of our materials. As I said a few minutes ago about the threshold strain that doesn't go from monotonic loading to cyclic loading, several concepts may not completely translate from what we are used to in monotonic to cyclic, so we have to reconsider some of them. Pepper, throughout the presentation, I put some scaling factors, and so these dimensional pi ratios appear everywhere in physics, and of course they're going to be very important here, and like the one for accelerated diffusion, etc., all of them, and these are just a sample of them, to define the domain where these are going to be important or not. If you're looking at the matrix, think of asymptotic states. They are very robust for engineering design. And they are different for volume and shear. Cyclic fluid flow, it appears for all the cases that we've done so far, but I'm not convinced that we can generalize it, that often becomes equivalent to fixed diffusion, but with a very unique diffusion coefficient that it captures an internal length scale of the material and the externally imposed time scale of the cycle. When is chemical, suction, electrical, and cycles, when are they going to be important? When the materials have high specific surface and at low effective stress. So we're talking about clay materials, clay dominant materials, and low effective stress, otherwise we can begin disregarding. For phase transformations, crystallizations, think of the difference between grain displacive versus pore invasive, because they will manifest completely different and implications are going to be dramatically different. Thermomechanical cycles are relevant at all sizes. And I didn't say anything about numerical modeling, but let me just say that if you are a modeler and you want to advance this time stepping, just one cycle would be a lot. 1 million cycles will be quite difficult. And furthermore, we don't have constitutive models. Let's say that if you are in plasticity, as soon as you push the yield surface out in the first cycle, you come back into the elastic domain. When you load again, you remain within the elastic domain. So you need new constitutive models. And what it appears now that the community is moving towards is some form of hybrid, that we bring some mechanics sporadically and empiricism and these asymptotic relationships to make sure that things remain stable and convergent without error accumulation. I have to say that it has been an honor being here, and I'm so grateful that you all were willing to stay until this time. I'm particularly grateful to Majid, and he has been such a force behind all this InterPore and an example to all of us, to the organizers and the support team, and once again to all of you, thank you.
So besides thanking Carlos for a lovely and enlightening talk, I don't quite know what to do next. And I'm not sure that there's, so I'll thank you. And I think we make room for the next round of people to close the meeting because they are more worthy of closing the meeting than the likes of me. But I would like to really thank the organizers. I'm sorry?
Questions.
Oh, yes. There is still time for questions, I think. So let's do the questions then. And this time I will show red cards to the questioners.
Well, let me say, please feel free to send me questions to my email. I look forward to that, and I promise to reply. But
so I'll have a question. So we are talking now in this time of global climate change about doing things which are actually relevant to our times. And I think that you have pointed out several such problems that involve human infrastructure and also behavior of natural systems, which will now be subject to unusual cycling and stresses and forces and what have you. Do you have any remarks for the young people here so that they focus on things which might be relevant to this very dangerous and transient time?
We know each other very well. I have the feeling that he knows the answer, but let me give it a try. I think that indeed I'm not apocalyptic. I think that difficult times are coming, and that the energy challenge is a global challenge, and that the inequality will be exacerbated. And I think that it's up to all of us, and particularly the young generation. I'll be gone by the time this reaches the critical times of the 2050. But it is a responsibility on all of us, not just to do good work, but to do meaningful work. the time there is a sense of urgency building up.
I kind of like the Tower of Pisa, which started leaning right away. So what did the people do? They continued building it up, hoping for the best, but never mind. Any questions from the audience? You can shout and I will repeat for the audience online because probably, oh, the microphones are here up front. I know that people are shy about stepping up, but please do ask some questions.
Majid, I think that, thank you. Thank you again.
Well, so now it's time.